Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Thank you and welcome back. And I would like to know, who was here last week? Can you please? Okay. All right, so I hope you remember what we did last week. I am going to briefly remind you throughout the talk. But the plan of the talk today is to start from some ideas about building models of universes using strings and brains. And then I'm going to go into talking about black holes and why black holes have been considered very interesting objects and somewhat problematic from a theoretical point of view for a long time. And then the progress that string theory has made in understanding them. And that will lead naturally into the connection between certain gravitational theories, so theories of gravity, and certain theories that are quantum mechanical. Finally, I will conclude with cosmology as a window of opportunity in the sense that cosmology might help us to find signatures of string theory. And depending on how much time I have, I might skip some of these sections. And finally, I want to mention that not next week, but on March 8th, Elena Razia, who's also in the physics department, will be giving a lecture talking about modeling the cosmos. So she will talk about cosmology in much more detail. So what we saw last time is that if you think about understanding a black hole, and you realize that it has a place that is called the event horizon, that is sort of the point of last return. So if you are traveling around near a black hole, if you make it past the event horizon, you will fall closer and closer into this very short distance throat, and you will approach a singularity, and you will never make it out of the black hole. And the reason why a black hole is called a black hole is because it's so massive that even light is trapped inside and it doesn't escape. Of course, I'm going to explain to you why this picture is not quite true. But the point that you should have gathered from last week is that if you want to understand this type of object where relativity is breaking down because the curvatures are so high, and quantum mechanics matters, you really need to have a theory of quantum gravity. And another place where quantum gravity is relevant is the very beginning of the universe. That's because the universe at the beginning was very small, so quantum mechanics was important. And it turns out that there was also high curvature. There was some initial singularity that causes a problem from the theoretical point of view. And last time I showed you that if you want to think about building blocks, some particle theorists like me think that there should be strings of membranes making up everything else. So if you imagine zooming in inside of the atom and inside of the nucleus and inside of protons and neutrons, you would see structure. So this is a picture of quarks. And that structure might be made of even smaller objects that are called strings, these wiggly things right here, and membranes that I'm going to call brains from now on. So anytime I say brain, just think of some sheet like this. It doesn't have to be two-dimensional, but visualize it as some sheet of paper that can bend. And so you have these strings that can be closed or they can be open. And these strings and these membranes you should think of as the building blocks of nature. Of course, we don't know that this is true, but this is one possible scenario which gives you a good theory of quantum gravity. So now I want to go back in time a little bit. It turns out that if you look at quarks, the things that are inside protons and neutrons, they don't like to be free. So this is supposed to be a picture of a prison. So you see little quarks inside. I did not make this, by the way. It's not very nice, but it gives you the idea. So imagine starting from a bunch of protons and neutrons. If you zoom in inside of them, you see that you find 3 quarks. And we picture them as being connected by some springs. The reason why we put little springs there is because if you try to pull them apart, they don't want to separate. So as you can see, they're really angry. They don't want to separate. They're resisting. And this is why we say that quarks are confined inside of protons and neutrons. Because if you try to pull them apart, they won't come apart. So this is an animation of two quarks. As they're trying to get farther apart from each other, they're pulled back towards the center. And don't ask me what this red thing is supposed to be. I have no idea. Again, this is an animation I got from the web. But think of it as you try to separate two quarks, they're pulled back. Now, strings were originally introduced exactly to describe this type of behavior. So people thought that if we put a string attached to two quarks, the string could tell you that as you're pulling them apart, they want to go back together. So it's really acting like a spring. So this is how the idea of strings was initially introduced, I think, in the 70s. However, it turns out that strings give you additional objects that were not needed, people didn't understand what these additional objects had to do with the theory of quarks. And eventually they came up with a much better theory for why they're sticking together. So there's some sort of glue that keeps them near each other. In fact, it turns out that they identified gluons, so particles that are supposed to carry this glue, as the objects that are responsible for the strong nuclear force. If you remember from last week, the strong nuclear force is the thing that is keeping protons and neutrons together. And of course, I'm being a little rough here, but that's the main idea. So strings were abandoned because a better theory came along, until later they realized that one of the vibration modes of the string is a particle that looks like the graviton, the carrier of the gravitational force. In fact, it's one of the vibration modes of a closed string. This is something we went over last week. And then, in order to reproduce the right strength of gravity, they took the strings to be much smaller. So if you take a string to be smaller than the one that people thought would describe two quarks, you realize that it matches very well with gravity and that it can describe a theory of quantum gravity. So after this, people started being interested in strings again, and they thought that by probing deeper into the structure of protons and neutrons and the structure of quarks, you might end up seeing these little wiggly objects. So there was a renewed interest in string theory, and of course, to explain quantum gravity. And with that came a lot of jokes. So this is supposed to be a conference, a string theory conference in 2000. And this woman is saying, I'm sorry, I know you've got charm, but I'm really into brains. So it turns out that charm is a type of quark. So she's basically saying, I don't really care about your quarks, I'm more interested in brains, which are string theory objects. So if you look on the web, you'll find lots of cartoons. Unfortunately, I couldn't find one that's really funny. The only one that I found that came close to being funny, the guys in Alpina have, and it's a little bit on the vulgar side, so I did not put it on the top. But they have it. Okay, so you can still use a string to describe what happens between two quarks. It doesn't give you a perfect description of quarks, but it comes pretty close to it. So if you remember that these open strings have to end on these membranes, and if you think of a string as connecting two quarks, you can build models of particle physics. So you can describe all the elementary particles that we see, or you can try to do that by taking some maybe complicated system of membranes and strings. And so this is called model building. A lot of people right now are working on it. So the goal is to build a model for our universe. So think of it as having a toolbox. You have some open strings, you have some membranes, you have some closed strings. So these are the tools at your disposal. And here is some open string that's sort of closing into a closed string and then detaching again. So just think of this as an open string wiggling around. That's a closed string. So you have these tools, and you can use them to build realistic models of our universe. So you can make some complicated arrangement of membranes with open strings that have quarks at the ends and closed strings. And you can try to describe our universe using this. And of course, this is a very difficult project because our universe is very complicated. The standard model is very complicated. And in some sense, our understanding of these objects is not that old. We only started learning about this recently. So remember that I told you that if you look at all the forces that we have, today we see gravitational force, we see electromagnetism, and then two forces that are responsible for what happens inside a nucleus, roughly. Remember I mentioned that these forces at our energies look different, but as you increase the energy, they start merging together. So this is the weak and the electromagnetic force coming together. At some higher energy, they meet with the other nuclear force. And even higher energies, we expect them to meet with gravity. So this was the idea of unification, that there should be a single theory that describes all of these. And string theory is living here. A very, very high energy, that's where string theory is becoming relevant. That's where we should be able to see strings. But the energies that we are probing today, or that we are going to probe in a few months at this experiment in Geneva, the LHC experiment, are much lower. So this is a particle accelerator. You take a bunch of protons, you send them in two directions, and eventually they bump into each other and they give off a huge mass of energetic particles. So these energies are tested right around here, so they're much, much lower. So one of the challenge is to ask if we can bridge those two theories. So imagine that this is as the energy is increasing in this direction, string theory lives up here. So it's a theory that works at very, very high energy. The experiment that I mentioned and the standard model of particle physics are relevant at much, much lower energies. And so we want to connect these two. We want to bridge them. We want to go from this very high energy theory to something that we can measure today. So it's not clear that we can bridge them. It's difficult. A lot of people are working on it. And the other question that you have a right to ask is whether experiments can ever test string theory. Now, I want you to understand that these are very different questions. So we may be able to do this and still not find experimental tests of string theory. However, most people, there is now the bridging process going from high energy to low energy is becoming better and better. People are coming up with models that are more and more realistic. And they're also thinking of ways in which we can find some of the footprints of string theory in this type of experiments. But we're not there yet. So this is a work in progress. So as I mentioned last week, we can't just produce strings at accelerators. We can't take protons, mash them together, and produce strings because the energies are not high enough. So what we can do is find some indirect ways to test string theory. So it's possible that some of the ingredients that are required in string theory would give you footprints that we can measure at these experiments. So this is called indirect testing. And one example of this is a new property that's called supersymmetry that people have introduced recently to solve a lot of the problems of the standard model. Turns out that supersymmetry, roughly speaking, tells you that each particle that we see, these particles up here, has a partner that we haven't seen yet. So think of, say, the proton. A proton would have a partner. Each particle that we have measured would have its own partner that we have not seen yet, but we expect to see them here if this property is really there. And this is also a property of string theory. Well, it's something that string theory uses every day. So you might ask, if I measure this, I'm in some sense learning something about the fundamental theory, the theory of strings. So just to give you an example of the type of games that people are playing, there are models where people assume that we live on one membrane. So this would have to be our four-dimensional world, 3 spatial dimensions and time. So this is where the standard model is. We live here. And then somewhere else, separated from us by the additional extra dimensions that string theory predicts. There could be other membranes where you might have some string theory ingredients. So imagine that here you have some property of string theory, and here you have the theories of particle physics that we know, that we have measured. It turns out that these two guys can talk to each other. One way that they can talk to each other is by having these little strings propagate back and forth. So these guys can carry information from one to the other membrane. So this is one way in which we might be able to see some of these ingredients somehow in our world. And one of the ingredients that we are hoping to see is this supersymmetry. So this is a cartoon that I think was, actually, this was published in a book by a Michigan professor in the Department of Physics. And I think he actually drew the cartoon and then he gave it to a professional to have, so that it would be put on his book. So it's a little bit hard to read. So this guy here, I think is Einstein. I mean, it should be Einstein. So he's writing down some theories that is then crossing out. And the one that wins is E equals mc squared, which we know is true. So over here is calculating basically general relativity. And over here, he writes down first superstition, then supernatural. Then there's something that I can't read. I have no idea what the third line says. Maybe Myron knows. No. And finally comes out with supersymmetry. Of course, Einstein had nothing to do with supersymmetry. This came out much later. But this is a very nice cartoon from Gordon Kane, who's here in the physics department. Okay, so now I'm going to switch gears and talk about black holes. So I've finished the section on trying to model our universe using branes and strings, and I'm going to talk about what string theory has taught us about black holes. Remember, a black hole is some very massive object, sort of like a ball that's sitting in space-time. It's so massive that it's pulling down very hard on space-time and causing a singularity. So anything that goes near it is going to fall inside and just keep falling down and down towards the singularity. And general relativity, the theory that Einstein developed, doesn't really work near singularities. It just breaks down. That doesn't mean that, it doesn't necessarily mean that there's something wrong with this object. It simply means that this is not a good theory to describe it. So we need a better theory. Now, it turns out that Hawking has told us that quantum mechanics is actually telling us that black holes are not completely black. So earlier I told you that light falls in and nothing comes out. Well, if you worry about quantum mechanics, you learn that that's not really true. Black holes emit radiation. And by the way, this is the reason why they lose some of their mass and eventually they evaporate. So think of them as, so this is a picture of a black hole and it's emitting radiation. And as the radiation comes out, the mass of the black hole is getting smaller and smaller and smaller. And this is how black holes evaporate and die eventually. So because of this radiation that's coming out of the black hole, they have a temperature and they also have an entropy. And maybe you don't know what entropy is, so I'm going to give you a rough explanation for it. I want to concentrate on it because it turns out that the entropy is very important and it tells us a lot about the structure of the black hole. So one way in which people sometimes define entropy is a measure of disorder. So you hear a lot of people saying, oh, and by the way, entropy never decreases. So you'll hear a lot of people saying, I don't really want to clean my apartment because I know that eventually it will get disordered again because entropy is always increasing. So I know at least one person who lives by this rule and is in the audience. So that is not a reason not to clean your house. The other way to understand entropy is that it's a measure of the microscopic, the tiny little things that are making up a system. I'm going to give you an example of that is not perfect, but it gives you the idea. So let's say that I take two dice. and I want to ask how many ways can I get one number out of them. So for example, if you want to get a 3 out of 2 dice, you can either get a 1 on this face and a 2 on that face, or the other combination. So there are 2 ways to get a 3. So this table is showing you that if you want to get the number 3, you can do it in 2 ways. If you want to get, say, the number 4, you can get a 3 and a 1, 1 and a 3, or a 2 and a 2. Right? So think of the number, the ways in which you can get that number as being these microscopic configurations. So they're the tiny little ways in which you can achieve something. And if you look at this, you'll see that the number of combinations is increasing as you get closer to 7. And 7, it turns out, is the number that you can get with the most amount of possibilities. So in this case, you would say that this guy, number 7, has the largest entropy. Largest entropy because you can get a 7 using the largest number of combinations. So these various combinations are what you should think of as the microscopic constituents. This is not a perfect analogy because these dice are big objects. So these are not really microscopic constituents, but it gives you the idea. So what about the black hole entropy? What are the microscopic things, little pieces, are making up a black hole? The entropy is a measure of that little structure. So if you can understand the entropy, you can start to understand what a black hole is made of. Now, there is a very old, important question that came up when people started learning about black holes. So I told you that black holes pretty much eat anything. So this is bread, that's an airplane, I don't know what that is.
Landmine?
Maybe. This looks like a satellite, maybe. So you get all these different ordered systems falling inside of a black hole. They're ordered in the sense that you know exactly what they are, except for that guy. So you know that there's some information here that's going inside of the black hole. So some of the questions that you can ask is, what happens to the stuff that goes inside? I mean, where does it go? The other question you can ask is, if I send in information, things like airplanes and pieces of bread, but I get out just random radiation, does that mean that I'm losing information? If you're losing information, that's a very big problem with quantum mechanics. It tells you that quantum mechanics is not right. And as my students know, since I'm teaching this class, we like quantum mechanics. So it would be a pretty bad thing if we had to modify it. We really like it. We are okay modifying general relativity, but we're not okay modifying quantum mechanics. Most people are not okay modifying quantum mechanics. So we really would like to think that the black hole does not eat information. It's possible that we just don't understand anything, and there's some other way that doesn't involve modifying quantum mechanics. But usually, information loss implies quantum mechanics is not good. So what we want to do is say, can we calculate the entropy? And what does that tell us about all the little things that are making up the black hole? So it turns out that in the 1970s, more or less, Hawking and then Bekenstein did some approximate calculations of the entropy. What I mean by approximate is that they used a mixture of general relativity, which is a classical theory, and quantum mechanics. And this was very important work. I mean, they really, it was not easy to do this calculation. So they realized that they could, combining quantum mechanics and gravity, they could come up with an expression for the entropy. But their expression is not completely right because it's only an approximation. But if you had the right theory of quantum gravity, then you would get the right answer, because a full theory of quantum gravity would be able to calculate the entropy precisely. And string theory is an example of a theory of quantum gravity, or at least we think it is. So we can use it to check the entropy of a black hole. And this has been incredible achievement for string theory. It turns out that you can describe a black hole by some complicated system of membranes and strings that are connecting, that are sort of, attached to one membrane or the other, or possibly connecting the two membranes. So some complicated system of membranes and strings describes the black hole. And it turns out that the entropy calculations match. So that approximate answer that Hawking and Bekenstein obtained is recovered by string theory, except the string theory, being a full theory of quantum gravity, went even farther and told you the corrections to that calculation. And so in some sense, we're now counting the microstates, the various combinations of the dyes that give you a number of the black hole. And so these branes and strings are giving you a microscopic quantum mechanical description of a black hole. This is a very, very big achievement for string theory. And it also seems to show that there is no information loss. This is not, again, it's not perfectly clear, but it seems that there is nothing wrong on the string theory side. So if you look at this combination of membranes and strings, there is no information loss. Of course, a lot of people are still working on this. So this, again, understanding black holes better and better is an active area of research in string theory. So this is a cartoon summary for a black hole. Imagine that this is your gravitational black hole. Please don't look at this part of the picture. So this corresponds to some system of membranes and strings. We can also explain Hawking radiation. So imagine that you have, again, a system of branes and strings. Now you have two open strings that are coming together. So one is coming from this end, the other one is coming from that end. When they meet, they give off, they join and they give off this closed string. This process is equivalent to the black hole radiating and decreasing its mass. So again, you have two guys. It's a little bit hard to see because this is a fast movie, but one open string comes in here, the other one from there. They meet here and they give off this closed string. And as this process happens, the black hole decreases the size because it is losing energy. Okay. It turns out that this correspondence, this connection between black holes and strings is not an accident. It's an example of a much deeper and more general connection or correspondence that tells us that certain theories that explain gravity happen to correspond to certain quantum mechanical theories that explain particles. So this correspondence is not true only for black holes, it's more general. So obviously the black hole is an example of a theory of gravity. And this system of membranes and strings, because you can think of these strings as ending on quarks, roughly, is an example of a theory of particle physics. So this equivalence is just a simple example of this more general correspondence. And I've actually done most of my work on aspects of this. I am not going to tell you why it's true. If you want me to go over it, I can do it at the end in the question session. I do have a slide, but it's a little bit complicated. So I'm gonna skip it for now. But the remarkable consequence of this correspondence is that we have managed to bridge those two theories that we thought could not communicate with each other. So we have connected gravity with quantum mechanics, and that is really incredible. Because that's the reason why people started, that was a big question that we started talking about last week. Quantum mechanics and gravity don't talk to each other, they're so different. Well, it turns out they're not that different. They can be related to each other. The reason why this correspondence is so useful and important is, one, because it gives you a quantum mechanical description of something that's gravitational, like a black hole, so you can learn about the structure of black holes. It turns out it's useful also for understanding singularities. The other reason why it's useful is because you can study, for example, things you don't understand on this side by studying things you understand on that side, and vice versa. So people are now trying to understand problems with, say, particle physics models, so problems here, by using their gravitational description. So it turns out that it's also a useful tool. The problem, or the challenge, is that the theories for which this correspondence has been shown to be true are not quite the theories that we measure in our everyday life. So these quantum mechanical theories are not as good as the standard model, and these theories of gravity are not quite our universe. So these, even though this is very important, we still have to extend it to setups that are more realistic. So building scenarios that are more realistic is, again, an active area of research and is a very important question. Okay, so I'm now going to switch again, and I'm going to talk about cosmology. And it looks like I'm doing pretty well on time, so we should be able to go through my entire talk. So it turns out that if you track the evolution of the universe, if you go back in time to the very beginning, that it started out by being very small, very hot, and very dense. So this is a picture of the evolution of the universe. It started out from something that we don't really understand, but we know for sure that it was small, hot, and dense. And then it expanded and it changed over time. And I'm going to go through some of the details of these changes. As it expanded, it also cooled, so the temperatures decreased as it became bigger. So if you want to go back towards the beginning, that translates into going to higher temperatures, or in terms of energy, it translates into going to higher energies. So if we are here today, if you go back towards the beginning, the energies became higher and higher and higher. And right here, they were incredibly high. And they were so high that you can ask whether string theory effects might have been important. So if string theory is the right theory of quantum gravity, then you know for sure that there were string theory effects around, because very, very high energies is where quantum gravity becomes relevant. And so right at the very beginning of the universe, you might expect to see some string theory signatures, if we could ever measure this. We'll find a way to take this measurement down to where we are today. Right, so things were very small. Quantum mechanics was important, where they were very curved, much like this. Curvature was very high, so general relativity was important. And so quantum gravity is the right theory that you need to describe the very, very beginning of the universe. Now, an idea that we have learned from quantum mechanics is that nothing can sit still. So space, in fact, there was a very young, somebody who looked like he was 7 or 8 last week, who asked a question if space-time can vibrate. I don't know if it's here today, but space-time does vibrate in the sense that it fluctuates. So imagine, let's say that we live on this surface, like this table. If you look really, really close to the surface, you will start to see little bumps. And if you look even closer, you see that the bumps are much sharper. So this is a picture of the space-time fluctuating. So notice that there are some ripples that are forming on the surface. So think of this as the space, and the ripples as being the fluctuations that I'm telling you about. So the space-time itself is actually fluctuating. You have these ripples that are forming. So at the very beginning of the universe, we had a period of rapid expansion. This is supposed to show you how the universe is inflating. So inflation is a period of very fast acceleration. So imagine that this is the universe, and these guys are representing galaxies or sort of structure in the universe. So think of them as galaxies. So as we are pulling apart, the distance between them is increasing and increasing and increasing and increasing, and it can get really large. And if we were doing this really quickly, this would be a period of very, very fast expansion. So notice that, let's do it again. So the distance is increasing. These guys are not really moving. It's sort of the string itself, the background that's moving. Was that on purpose? Okay, so we managed to kill the universe. So during this period of rapid expansion, the ripples that were started out by being very small were stretched and became large. So this is supposed to be a picture that explains inflation. So imagine that you're living on this balloon. There's nothing outside of the balloon. So the fact that there's blue here, just disregard that. Imagine that you live on the balloon and there's absolutely nothing outside of it. You're confined to the balloon. And the points, these dark points, you can think of as galaxies, or anything that is sitting on your balloon in your universe. And this is what I drew as a little ripple, quantum fluctuation. So as the balloon gets bigger and bigger, the distance between these points gets bigger, and the size, the wavelength of this little wave also gets stretched. So this explains how the universe is inflating, and the small ripples are getting bigger and bigger and bigger. So this, again, is telling you how the universe changed over time. So we started from something that we don't really understand very well. You then had some small fluctuations, period of rapid expansion that gave rise to what I will describe in a minute is the cosmic microwave background radiation. And 13.7 billion years later, you see galaxies, and we live right now. So in this first period, when inflation was working, the universe became suddenly incredibly large. So it went through a period of very, very rapid expansion. And notice that these galaxies that you see are actually due from they really come from the small ripples that I showed you. So they're a result of those little quantum fluctuations. So if you didn't have the quantum mechanical effects that gave rise to those fluctuations, you would not see the structure that you see today. We would not be here. Galaxies would have never formed. Okay. So as I mentioned, we start from these little wavelengths, little tiny wiggles. They get larger thanks to inflation. And today, we basically see their effects when we look out at the sky in the form of the cosmic microwave background radiation. So it turns out that there is some radiation that's left over from the very early universe, the time of the Big Bang. And this radiation is called the cosmic microwave background radiation, and it's sort of telling you that even though the universe looks smooth and uniform, it's not perfectly smooth, it's not perfectly uniform. There are some temperature fluctuations that are very small, but nonetheless are there. And you can measure them, and they really are a result, a consequence of the fact that you started with these quantum fluctuations. And I am not doing a good job explaining inflation because this is not the goal of my talk. There are a lot of questions that you can ask about inflation. It's a very deep, complicated process. I'll be willing to answer any questions later. But remember, I want to tell you about string theory, not necessarily inflation. And you will hear more about this next time. And I think even from Dragan Hutter, who's in the audience later on in the semester. Anything that was not clear? Go ahead.
Maybe you're going to cover this later, but I'm wondering how exactly does a vibrating string manifest as a force in the macro universe? What is it about the vibration that makes it?
Right, so it's actually the interaction between the various strings that you should think about as forces. So much in the same way that if you take two particles, like two quarks or a proton and an electron, the force between them is, you can understand it in terms of how they're interacting with each other.
So does the energy come from the vibration?
Okay, so good. So there is energy, yes, each vibration mode has a certain energy.
Okay.
Yep.
And they would have to all vibrate at their resonant frequency, and so if particles don't have the same resonant frequency, they just would interact. How it works?
Well, it's more complicated than that. But different frequencies would give you different particles, and then the way in which they interact depends on the specific properties of that particle.
If there are strings that live, excuse me, on that other stringy brain, and they are apart from us along some extra
Right.
large dimension,
Yep.
where are they?
Well, you told me, right? You just told me they're apart from us in some extra large dimension.
But in which direction? Which of the three dimensions that we can move in?
All right. So the extra dimensions are always perpendicular to our direction, right? So think about living on this table. If you are confined, if you're a little ant confined to this table, you might not realize there's an extra dimension pointing up. So we can't visualize anything higher than 3 spatial dimensions because we can't see them. But think of them as just being perpendicular to our dimensions.
So if they coincided with us, we could see them. But if they're not exactly where we are, we can't sense them, unless there's some interaction between the brains.
That's true, right. So it's the interaction between the brains. And the way that these brains interact is by exchanging those closed strings. So the closed strings are actually carrying gravity. So because they're gravitons, one of the vibrations is a graviton, the way that they interact with each other comes from the fact that you have this closed string moving, carrying information from one brain to the other brain. The real idea that I want you to understand is that this cosmic microwave background radiation is a picture of the early universe. The reason why it's a picture of the early universe is because, as you probably know, light takes some amount of time to travel. So what we see today is a picture of what happened a long time ago. So precisely 380,000 years after the Big Bang, this radiation, these photons, stopped interacting with everything else that was around them. And a picture of that time is what we measure today. So we're seeing the universe when it was 380,000 years old. So there's a lot of information in this picture. So if you go back to the idea of our small ripples, because these ripples started out by being very small when the universe was tiny, they can carry information about string theory. This is a possibility. So today there are a lot of people who are trying to ask whether some of the consequences of these little fluctuations can be measured in the CMB radiation. The other thing that you can do using cosmology is you can rule out some of the string theory models. Obviously, string theory can predict many, many different models. They are not all necessarily true. So you want to use the data, the cosmological observations, to rule out the string theory descriptions that are not accurate. So ways to do that are to ask whether string theory can give you inflation. If it turns out that inflation really existed, then we need our fundamental theory to be able to give you a theory of inflation. String theory has some trouble doing that. So for example, if you cannot get inflation or you can only get it in certain specific setups, that's very important to understand better the structure of string theory. Also, the type of gravitational waves that you get out are an important way to test string theory. As you know, we still have not measured gravitational waves. So, if we do measure them, we'll get a number, and you can compare that number to the number that you would get from a fundamental theory like string theory. So these are ways in which you can try to test the signatures of string theory at the energies that are around today, using experiments that we build today. Another reason why cosmology is a window of opportunity is because cosmology, through this process of inflation that blows up tiny things to large scales, is really our strongest microscope, because it gives us a picture of what happened a long, long time ago where energies were incredibly high. Those energies are much higher than the energies that we can reproduce at particle accelerators. So in some sense, this is really our strongest microscope. Again, the big challenge for string theorists is to make more realistic models. We have models that are pretty simple right now, and dealing with things that change in time is very difficult in string theory. So a lot more work needs to be done to describe cosmological processes. I think I have about 5 minutes left. I'm going to talk about the last part of the talk. It turns out that one of the strange predictions of string theory that has received a lot of attention lately is the fact that the theory predicts many, many possible universes. It doesn't just give you one model. It's a very rich theory, so it predicts a huge number of possible universes that could, in principle, be there. And this is a picture that is supposed to symbolize the various possible universes. So you should think of every valley. So there's one here, one here, one here. Anytime that you have a minimum or a valley has a place where you have a different theory. So for example, it's possible that this valley describes our own universe, but then you would have other valleys that would describe other universes. So this is something that is coming out from the mathematical structure of string theory. There's a lot of freedom to get a lot of different theories out of it. So some people don't like this. So there are several ways in which you can think about it. For example, you can say, well, I have this rich landscape of possible universes. I should study it. I should understand what the properties of that landscape are. Maybe life is only possible in some of those universes. Maybe some of them are just not realistic. They're not consistent. So you can study all the properties, see which ones are allowed but not like ours, and so on. Alternatively, you can say, well, maybe we just don't understand this landscape of possible universes well enough. It's just too early. We haven't done enough work. So we should look for mechanisms that can tell us that only one of those universes is possible. And there are people working on both of this. They're both important directions. I've done work in this area, and I am currently doing a little bit of work in that area as well. But the idea that you should get is that given the fact that this picture is there, we need to understand it better, but also find ways to rule out a lot of these valleys and say only one of these is a real good valley, and everything else is an artifact of the fact that we don't really understand the theory. So there are these two different possibilities. Okay. So I want to conclude by telling you that there are many things that we don't understand. And when I say we, I don't mean string theorists, I mean theorists. In physics, we have big questions that are completely not understood. It turns out that if you look at the composition of the universe, let's put it that way, that the things that we are made of, stars, things that we're familiar with, protons, gas between various galaxies, only make up about 4% of what we see. Sorry. About 4% of what we see. That most of it is made of something that we call dark energy, that is responsible for the fact that the universe is accelerating today. So this thing that we don't understand is driving the acceleration of the universe today. And then there is another large chunk that is so-called dark matter. So this is some sort of matter that is called dark because it doesn't, we don't see it, basically. It has strange interactions, so it's not really interacting with photons, we don't see it. And we have some ideas for where it may come from, but we haven't, there is no concrete. Well, there's some theories that explain it, but it's still a big question mark. Dark energy is an even bigger question mark. So I want to leave you with the idea that there's a lot of the universe that we do not understand. So you shouldn't be, you should be positive about supporting fundamental physics, because we really, and again, I'm underlining this. This is not a problem of string theory. This is a problem of physics. We really don't understand a lot of what is around us. So we have done a huge amount of progress, but there's a lot more work that we have to do. And Elena Razia is going to talk on March 8th. I'm sure we'll talk about this. Okay. Oh, by the way, if you Google string theory, you're going to get this spaghetti and meatballs guy out. I don't know why, but you're going to get him, and he has a message to tell you in the next slide. But before his message, let me summarize. So I hope I've convinced you last week that we really need a theory of quantum gravity. This is not a luxury. This is something that we need. String theory is a candidate. It may not be right, but for now, it works. It does the job. So we might as well use it. Then string theory has given a lot of understanding into the structure of black holes and the fact that gravity and quantum mechanics are connected for some special cases that we need to understand more. The main challenge is really coming up with models that are realistic. It's difficult to describe things that are changing in time, like the universe that started small and then went through a lot of different transitions. Connecting string theory to cosmology is difficult. Also coming up with realistic particle physics model is difficult. But there has been a lot of progress. People are working on it every day. And if you track down the amount of publications and the impact on progress in physics, you will see that slowly things are coming together. It's just taking a long time, but it's working. So now I'm going to leave you with the spaghetti and meatballs guy, and I want to thank you. Thank you for coming for 2 weeks.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.